So, all right, welcome back. So today we're going to talk about block diagram algebra. So please let me know if the audio and video quality are fine. That's going to be our topic today, and this is lecture 2. All right. So once again, good morning to you all, and if you have any query during the class, make sure to ask them in the chat. I will be trying my best to answer all of your questions. And during the stream, if you encounter any issue like audio syncing issue, something that happened in the last class, I completely missed that part. So if you encounter an issue like that, please let me know in the chat. Okay. And also, if you don't understand something during the class, make sure to promptly ask me, right? So I would assume that you attended the last class, and based on that assumption, I'm going to proceed. So we're going to kind of going to take a bit of the discussion that we did in the last class, and also in the last semester, right? So in the last semester we studied signals and systems, and there we studied quite a few things. So we are going to I should say we are going to actually use that knowledge as well. Okay, but in any case, whatever we need, we're going to derive it properly in our classes as well. So don't worry. So today we're going to talk about block diagram algebra. So last day I introduced you to two different paradigms of modeling. Okay, so modeling is essentially one of the most important parts of control system engineering, and in the last class I introduced you to modeling. All right, so then there are two paradigms of modeling, right? I said there was one paradigm called the glass box approach or the white box approach, and another paradigm is the black box approach. All right, so in the glass box approach, you know everything that is there to know about the system. You know the internal construction, you know how every internal component interacts with each other, and based on that you could calculate the response of the system given a certain external input. All right, so that is something you understand, right? And then the black box approach actually removes all the complications of the internal dynamics and everything. It only tells you the relationship between the output and the input, right? So essentially, in a black box in the black box approach, we essentially draw a box like that, and we call, okay, this is our system, and this system interacts with external inputs, okay, and generates outputs. All right, so that is something we actually define in a very simple black box model, right? So let's say the inputs are defined as xt and the outputs are defined as yt. All right, so if that is so, then we know that if the system is a linear time invariant system, and yes, that's the type of system we are going to discuss for the most part in this course. Of course, we are going to actually have some time dedicated for discussing systems that are not linear or not time invariant, but for the most part we are going to talk about systems that are linear and time invariant. All right, so this discussion that we are going to do today is applicable for linear and time invariant systems. Okay, so let's consider this is a linear and time invariant system. All right, so then we know that if we know the impulse response of the system, which is denoted by ht, then we know that the output of the system can be mathematically calculated as the convolution of the impulse response of the system and the input to the system. All right, so just to remind you, what is the impulse response, what is ht? Ht corresponds to the output of the system when the input is a unit impulse signal delta t. Okay, so if I excite the system with a unit impulse signal delta t, the output of the system will be ht. So this output is called the impulse response, and as a matter of fact, we actually have proven this earlier in our earlier semester, that if we know the impulse response of the system, then we actually know everything that is there to know about the system for an LTI system, right? So the impulse response encapsulates the entire behavior of the system. So if we excite the system, also we derive that if we excite the system with any arbitrary signal xt, and if the impulse response of the system is ht, then the convolution of ht and xt gives me the output of that system to this input. So that is something we do, right? And then what we did, we applied Fourier transform in our last class on our signal systems. We applied Fourier transform on that, and then we realized that the Fourier transform of the signal yt, of course, we denoted that with y omega, and then we actually derived the fact that the Fourier transform of the convolution of two signals is the Fourier transform of the product is a product of their individual Fourier transforms. The Fourier transform of the convolution of two signals. So essentially, if I take the Fourier transform of this whole thing, it will be the Fourier transform of this multiplied with the Fourier transform of this. So the Fourier transform of the convolution of two signals is equal to the product of their individual Fourier transform. So something like that we actually figured out in our last discussion, right? So we applied ft on this. So Fourier transform. All right. Similarly, we are going to prove in this class as well that if we apply Laplace transform, a very similar result appears. So considering the Laplace transform of yt to be ys, and considering the Laplace transform of ht to be hs and xt to be xs, then the Laplace transform of the convolution of ht and xt is the product of hs and xs. So a very similar result actually appears if we apply Laplace transform. And in this course, we are going to actually use Laplace transforms instead of Fourier transforms. And I'm going to explain why we are going to use Laplace transforms instead of using Fourier transforms. So we can just say this is applying Laplace transform instead of applying a Fourier transform. All right. So that is something I think is understandable. Again, we are going to actually derive this in due time. So don't worry. All right. So instead of writing the system this way, what we instead do, we apply a Laplace transform on the whole thing. And this is what we do. And again, this actually has a few conditions with it. We're going to explain that in due time. But let's assume that we are assuming all the initial on all the conditions are being satisfied. Okay. So there are a few conditions that need to be satisfied for these things to work. But we're going to assume that those conditions are satisfied. Once again, let me repeat, if you encounter any confusion during the class, make sure to ask me. All right. So once again, we are only talking about linear and time invariant systems that are both linear and time invariant. Okay, that's the condition we are imposing. And instead of doing this, what we are saying, instead of writing xt and yt, let's talk about their Laplace transforms. Or you could talk about Fourier transforms as well. All right. So the idea is that if we also do the Laplace transform for the impulse response, which is something like hs, then we can say that the output is nothing but hs times xs. All right. So hs is the Laplace transform of the impulse response. All right. Something like that. So this pretty much acts like a gain, like an amplifier. So essentially, this system that was described by a differential equation probably, okay, can now act as an amplifier. Okay, something like an amplifier. So essentially, whatever gain this provides gets multiplied with the signal and gives you the output. So this is kind of like an amplifier, right? So in the frequency domain. So this is again called frequency domain. I'm going to explain these terms in proper details as the course progresses. And also I understand that we discussed some of it in our signals and systems classes. All right. So that's the understanding here. All right. And given the fact that the same thing happens if we apply Fourier transform or Laplace transform, we can actually, rather I should say confidently and conveniently, we can get rid of. So this is again the notation that we're going to use. We can get rid of this s. Okay, the implicit variable s. We can get rid of that. We can just say, okay, the impulse response is denoted by h. Of course, the Laplace transform of the impulse response is denoted by h. The input is denoted by x, but it's not the input in the time domain. It's the input in the frequency domain. So probably the Laplace transform of the input, and the output is y. So notice the capital letters here. So we are expressing them using uppercase letters, not the lowercase ones. All right. So that's again something that can be understood very easily. So this is again gives you a very easy to write notation, right? So if we just write y equal to hx, that's easier for us to write than using all those implicit variables. So y is a function of s, h is a function of s, x is also a function of s. Okay, so that is something that has to be assumed. All right. Any confusion regarding this? All right. So if you don't have any confusion, let's proceed, right? So let's talk about certain topologies here. So we talked about one topology in the one standard topology, the feedback topology in the last class. And here, let's talk about a few more topologies, and we're going to learn how we can actually use certain simple algebra, right, to simplify complicated systems, complicated models, right? Yes, somebody asking, is it still in the Laplace transform form? Yes, I mean, they are still in Laplace transform form. So we are just omitting this s. We are not just writing s. We are just omitting that fact. Okay. But it's there. I mean, writing s everywhere is kind of a redundant thing. Okay. If it is understood from the context that, yes, you are using the Laplace transform version, yes, so then it's fine. But notice the capital letters, the uppercase letters are denoting that these are the transformed version. So this is some sort of a transform, either a Laplace transform or a Fourier transform. But these are not in the time domain. So this is not like xt, this is not like yt, something like that. Okay, just keep that in mind. So whenever you are using an uppercase letter, you have to understand that these are denoting the transformed version. Okay, because if these were yt, function of time, if these were all functions of time, then this multiplication would not have happened, right? Instead, the result would have been found through the convolution. Okay, let me just write down the expression for the convolution. So again, we're considering linear time invariant systems. So anyway, so the result is h tau x t minus tau d tau, that integral. Okay, or the other way around, you could write x tau h t minus tau d tau. So that integral would have been done. So again, so that's quite understandable, I believe. Alright. So now let's talk about some simple topologies regarding control systems here. Alright. So let me know again, once again, if you have any confusion regarding what we are discussing right now. So some basic topologies. Rather, I would say configurations. Okay. So the first configuration that we are going to talk about is a cascade configuration. Okay. So what is a cascade configuration? Let's say we have a system. Again, we are using black box approach. We're just describing the system. We don't know what the system has inside. We're just saying that the system is described through this function, capital H. Okay. So that if we know the Laplace transform of the input, we can actually calculate the Laplace transform of the output. In other terms, if we know the input, we can actually calculate the output. Because if we know the input, then we can actually, so if we know the input xt, then we can calculate the Laplace transform of the input, and that gives you xs. Okay. If we know the function here h, which is the Laplace transform of the impulse response, then we can multiply x and h and calculate the Laplace transform of the output. And then again, in order to calculate yt, all we need is to apply the inverse Laplace transform on this. So this is kind of again internally assumed. You have to understand that. So just describing this h, okay, we can actually rather describe everything that is there to know about this system if the system is linear and time invariant. Okay, so again we are talking about linear and time invariant systems, and for the sake of notation or similarities in notation, we shall not call them h, we are just going to call them by the term g. Instead of calling them h, we are going to call them g. And just to make sure that we are on the same page, I'm going to describe this later on. Just keep in mind that this h omega, we discussed this in the signals and systems classes. This h omega is known as the frequency response function. This h omega is known as the frequency response function. So the Fourier transform of the impulse response is known as the frequency response function. And this hs, which is the Laplace transform of the impulse response, is known as the transfer function. Again, don't worry, we are going to have a complete dedicated class on discussing these things shortly. So don't worry about that. Just keep in mind that hs, which is the Laplace transform of the impulse response, is called the transfer function. All right. So again, the name is very easily understandable, because if we have the input, you can multiply that with the transfer function and you get the output, of course, in the frequency domain. Okay. So if you have xs, the Laplace transform of the input, you multiply that with the transfer function, you get the output. So it kind of transfers the input to the output in a sense. Okay. It kind of transfers the input to the output. So that's the idea. Yes, G is just a different name for a transfer function. This is just for keeping, what should I say, the convention the same. Okay. Gs is again a transfer function. Hs, all these things are transfer functions. Okay. Whenever I take the Laplace transform on the impulse response of any system, we get the transfer function. Okay. So Gs is the transfer function here. Of course, that's understandable that for this system, the impulse response was expressed as gt. Okay, this system had an impulse response gt, and that's why the Laplace transform was written as gs. That's a convention. And of course, the Laplace transform of the impulse response is known as the transfer function. So that is understandable, I hope. Right? So let's say the input here is xs and the output here is ys. Right. Again, I'm going to simplify writing these things. I'm not going to write s everywhere. Okay, just for this ones, I'm writing this s here. So we know that the output is ys, and that's given by gs times xs. That's not a concern here. That's a very easy thing to understand here, I hope. Right. But let's just say this is, instead of being gs, let's say this is, so I'm going to skip this, skip writing s. Yeah? So this is x and y. Let's say this is g1. Okay, some other transfer function. Okay, in that case, of course, y would be g1 x. Pretty simple to understand, right? I guess. But let's say we have another block which is taking the output of the first block, okay, as the input in the next one. So we have another block that is taking the output of the first block as the input. So whatever output goes out of that becomes the input of the second one. Now, question is, if this is the output, we are calling that y. What is y? In order to understand this, we have to figure out what this input was, right? What this signal was. And of course, since we are again talking about Laplace transforms once again, the same thing here. So here, whatever signal I have in between, which is the output from the G1 block, and that acts as the input to the G2 block. What is that? That's just G1. That's just G1 times X, right? That's G1 X. And that appears as the input to the second block. And obviously, if that is the input to the second block, then what is the output of the second block? So this is the input signal to the second block. The output would be this multiplied with the input signal. Of course, in the frequency domain, these are all functions of S. So this is going to be G2 G1 X. All right. So we can say this Y is nothing but G2 G1 X. And multiplication in this case is commutative in nature. So I can always write something like G1 G2X to clean it up, sort of. So that's understandable, I hope. And of course, whenever we are talking about this, then we write down the full version. The full version is ys is equal to G1s G2s X. All right. Yeah, not just G1 times G2, but G1 times G2 times X. All right. So that's the output. I don't think there is any confusion here, right? All right. No problem there. But now let's talk about a system, another system. And in this system, we don't have two blocks, but let's say we have another system. We have another system whose transfer function itself is expressed as g1 times g2. Okay, and the input is x, the output is y. Oh, someone is asking, why do we do Laplace transform here? Yes, I'm going to explain why we use Laplace transform instead of using Fourier transform. Okay, I'm going to explain that when we introduce Laplace transform to this. Just keep in mind that the same thing, the exact same thing, today, whatever we are going to talk about, we're talking about, the exact same thing happens if we applied Fourier transform instead of Laplace transform. If these were just y omega, g1 omega, like that, the same thing would have applied exactly without any modification. Okay, without any modification, the same thing would have applied. But instead, still yet we are going to apply Laplace transform. We are just using Laplace transform instead. The reasoning will be explained later in a later class. Okay, next week we are going to explain the reasoning next week. So just keep in mind. All right. Now with that, with this one right now, so let's say we have another system where the transfer function is instead g1 times g2. Okay, let's say the transfer function is instead g1 times g2. Under that scenario, we know that again the output has to be equal to whatever the input is, of course, in the transform domain, and multiplied with the Laplace transform of this. So essentially g1 times g2, whatever the impulse response is. So g1 times g2 times the input. So that's going to be the output here. And you see that since we are using a black box approach everywhere, we are only interested about the whole thing, right? We are only interested about the whole thing. So in a sense, we are only interested about this whole thing, right? Because if we think about this, that x is the external input that is appearing here, and y is the external output, and this thing that I have drawn in this dotted green box here, and if we think about g1 and g2, then these are the constituent parts of this box here, right? If you think about this, right? So in the black box approach, again, our idea is to simplify everything so that we can actually tell the relationship between the external inputs and the external outputs, disregarding whatever is there inside, right? So in this approach, we can say that yes, that these two blocks that are cascaded with each other appear to work like a single block that has a transfer function g1 times g2, right? So these two cascaded appears to have the same functionality as far as the input and output is concerned, with this one, right? So we call it an equivalent representation. So the whatever we have here is equivalent to whatever we have below. So that's an equivalent representation. Okay, and as such we can actually rather simplify this, or rather extend this to much larger blocks here. All right, so let's say we have, instead of having two blocks in cascade, let's have n number of blocks in cascade. Okay, yeah, so n number of blocks in cascade, and say this one has a transfer function of g1, this one has the transfer function of g2, this one has the function of g3, and there are so on and so forth, and this one has a transfer function of gn. Okay, so different transfer functions. So if x is the output input and y is the output, then obviously you know that the signal here will be x, so g1x essentially, and that acts as the input to the second one. So the signal here will be g2 g1x, Same thing. The signal here would be G2, sorry, G3, G2, G1X, and so on. And finally, the signal would be Gn, Gn minus 1, whatever, dot, 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 G3, G2, G1X. In other terms, we can actually rather clean this up and write it as G1, G2, G3 up to Gn times X. Right? That's going to be the output of the system. So this is technically equivalent to having a system. This whole thing is equivalent to having a system whose transfer function is G1, G2, G3, dot, 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 Gn. Because as far as the input and the output are concerned, these two systems do have the same relationship. So if I consider this whole thing to be inside a box, and if we consider that we are only interested about the relationship between the input and the output, then having this system inside the box and having this single system inside the box, they are going to produce the same relationship between the input and the output. So we are going to say these two block diagrams are equivalent. So any diagram that has these functional blocks, it's called a block diagram. Okay. So a diagram containing this blocks here. Okay. This blocks here is called a block diagram. So all these things are block diagrams. So these two are equivalent in nature. Understandable, I guess. Okay. Now try to understand this very idea is that we are figuring out the equivalence in terms of input and output, right? So that this system, if we excite this with a certain input, produces a certain output. Now this system, if I excite this system with the same input, it will produce the same output, right? So this is called input-output equivalence. The input and output remain unchanged. Okay, so if I keep the input unchanged, the output will also stay unchanged. So these equivalences are input-output equivalence. Okay, and that's the same thing that we do, for example, for basic electrical engineering as well, right? So when we combine two resistors, two capacitors, two inductors, things like that, we use that same idea, right? So in a combination or in an equivalent circuit, if we apply the same voltage across the element, okay, across the equivalent element, you will get the same total current, right? Same total current. So that's the same idea here. Very simple. So this is called a cascade block. Okay, cascade equivalence. Right. Now let's talk about the parallel equivalence. Again, once again, if you have any question during the class, make sure to ask. Okay, I think before I talk about this, I shall need to talk about yes, someone is saying talking about the transfer functions. Yes. So if we excite this system, for example, with a certain input and get this output, in order to have a single system that takes the same input and produces that output, exactly the same output, we need to have this transfer function. So these two are equivalent. Okay. For example, if we have a resistor, if we have two resistors here, okay, R1 and R2, and excite them with a certain voltage, okay, say V, okay, and I current passes through. So the voltage source here sees that I amount of current is passing through. It is equivalent to having a resistor R1 plus R2. Okay, so the thing has changed actually, but the thing is, if the voltage source is still producing V voltage, it will still be delivering I amount of current. Okay, so as far as the voltage source is concerned, nothing has changed. As far as the voltage source is concerned, nothing has changed. Okay, because in the input output convention, you know that voltage source is producing the input and the output is essentially the current through the circuit, right? So if I apply the same input voltage, I get the same current in the circuit. So that's the output, response of the circuit, response of the system. Even though the system has internally changed, but since these two are equivalent, as far as the voltage source is concerned, okay, the input and the output are the same. So same voltage source, same voltage produces the same amount of current. So that's called equivalence. Here, similarly, as far as the input and output are concerned, if X remains the same throughout this, Y will also be exactly the same. That's why we are saying that these two are equivalent. Yes, having these blocks in cascade is exactly equivalent to having this transfer function. Alright, so exactly equivalent to having this transfer function. Got this? But I think before I talk about these, let's talk about the different summing blocks. Summing and comparator blocks. Okay. Some additional blocks are there in the block diagram algebra, and here they are. They are represented with circles with a cross symbol in it, with an X symbol in it. Okay. So these are the different types of summing blocks. All right. So the idea is that they will take inputs, okay, and they will produce outputs. So for example, these two inputs are coming here, okay, and they will have certain symbols representing what happens with that input inside there. And later on, we are going to implement op-amp based circuits to actually do these things physically. Okay. So the idea is that if I get a signal, for example, calling it R, and if we get a signal, say calling it B, okay, then whatever signal that comes out of this will be R minus B. Okay, that's understandable, I hope. The same thing can happen, but in a slightly different fashion. It could have a plus sign, it could also have a plus sign. Okay, the output that we're adding, so for example, if this is R and this is B, the output is going to be R plus B. All right, same thing. All right. Similarly, in some other convention, you can use up any of the blocks. So for example, I can say, okay, I am getting one signal here, another signal here, and another signal here. It could take multiple signals. Okay, it doesn't matter. Okay, so let's say let's call this signal A, let's call this signal B, and let's call this signal C. Okay, these are, once again, keep in mind, all these things are Laplace or Fourier transformed. I'm writing capital letters. So essentially, R is nothing but Rs, okay, or R omega, which is the Laplace transform of RT. Just keep that in mind. Don't forget that. Okay, and let's say this is plus, this is minus, and this is also minus. Now, obviously, the output that will be B minus A minus C. You understand this, right? This is very easy to understand. Yeah, what about the, yeah, I'm just giving you examples. I'm just giving you examples. There can be infinitely many possible options here. Okay, there can be infinitely many possible options here. As I understand that you understand this, right? For example, the arrows can be in any possible direction. Okay, the arrows that are going in are the inputs to these blocks, and arrows that are going out are the outputs to the block. Just keep in mind that there can be only one output out of a summing block, okay, or a comparator block. There can only be one output out of a summing or a comparator block, okay, and okay. So for example, it could be plus, it could be plus. This signal could be R, this signal could be B. So I have another R plus B. Okay. All right. Yeah, what about, yes, that's a very good question. What about more than 3 inputs? Yes, if we have more than 3 inputs, then we have a generalized notation. I'm just going to draw that shortly. Okay. So this block here, which compares two possible signals, two signals like that. Okay, just keep in mind that it could have also been drawn in a very different way, slightly in a different way. I could have written this as a minus sign here. Okay, so that be something like b minus r. Okay, something like that. So anytime you are subtracting one signal from another through these kind of blocks, anytime you are subtracting one signal from another through this kind of blocks, we call it a comparator block. So essentially it is comparing two signals. So that's why it's called a comparator. Okay. But anytime we are doing anything else, like manipulating three signals, okay, or adding two signals, or again adding two signals here as well. In general, they are summing blocks, because what is subtraction? What is a minus b? A minus b is nothing but a plus of minus b, right? In general, everything is addition. Everything boils down to addition, right? So that idea gives you the fact that yes, these things are in general called summing blocks. All these are summing points or summing blocks, but they can have different signs. And if one of them is plus and the other one is minus, so if there are two inputs and one output, of course all of them have one output only, okay, single output, but can have multiple inputs. Under this scenario, if one of them has a plus sign, one of them has a minus sign, then we call it a comparator. It's a special type of a summing block, but in general all these blocks are summing blocks. Question is, what if we have more number of inputs than these? Okay, the idea is not to actually make a circle and draw something like this. No, that's not the idea. Okay, the idea is to again use a generalized context in this. And if we have multiple inputs, then instead of drawing it as a circle, we draw it as a sort of a vertical oblong type of box here, sort of vertical type of box. And here under these, say we can have n number of inputs. The output is always going to be only one there. Okay, and let's say these are some signals like I'm calling that this to be x1, this to be x2, x3, and there are n number of inputs, so xn. Okay, so this is again another summing block, because it is again using the generalized context here. Okay, and say this one is plus, this one is minus, this one is also minus, say, and last one is plus. I don't know. Okay, this is just a convention. So these symbols are giving you that particular notation here. And the output here, let's call this y, for example. The output is going to be x1 minus x2 minus x3, I don't know, and so on. Okay, and so on, and then ultimately plus xn. Okay, whatever. So that's understandable, I guess. That's again your summing block. Again, that's a generalized summing block. All right. So with that being said, let's go back to what we were actually discussing, the parallel architecture here. Okay, let's call this a transfer function g1. Okay. Let's call this a transfer function g1, and let's call this one g2. All right, and the signal that is coming in is actually kind of a split into these two, but again, this does not degrade. We are assuming quite a few things. When I split the signal, it does not degrade. Okay, so if the signal is x here, it is still x here, it is still x here. So you are tapping the signal. Okay, and this is a summing block. So I have a plus sign, I have a plus sign here. Nice looking summing block. No problem there. And now tell me, what is the output of this? Quite obviously, all we need to do, we need to figure out the signal at this point and the signal at this point. So here the signal would be g1x, and here the signal would be g2x. And through this summing block, we are adding these two signals. So the output of this, if I call this y, the output of this would be g1x plus g2x, obviously. And then we can actually factor out the x. That way we are going to have g1 plus g2 x. Right? So that way we can say this is equivalent to having one single system whose transfer function is g1 plus g2, and that is being excited with the same input x and it is producing the same output y, which is going to be equal to g1 plus g2 times x. Yes. So if I once again consider this whole thing to be inside a black box, so that I am only concerned about the input and the output, or the relationship between the input and the output, then we can say that this is the equivalent structure, the equivalent transfer function. So whatever I have here, the equivalent transfer function is this. Now obviously this can be further generalized. This can be very easily generalized to any number of possible inputs. I think you can understand that if I have a minus sign here, that will give me a minus sign here, and the equivalent would be just a minus sign with a minus symbol here. Just to give you the same copy. Similarly, another example, let's say I have a minus sign here. Say I have a minus sign here. All right. Sorry. Where did I get the minus sign? That's not done. Let's say I have a minus sign here. All right. Say I have a minus sign here. Nice. All right. So if I have a minus sign here, then obviously the output will have a minus sign here. That's obvious, right? So if I have a minus sign here, then that indicates that g1x gets up here and g2x is subtracted from that, and that gives you y. Now obviously the equivalent model would be g1 minus g2 instead. That's obvious, right? So that's again a very simple thing to understand again. Okay, so let's talk about the generalized version of this. Say we have n number of systems that are in parallel. Say we have n number of systems in parallel and the first one has a transfer function of g1, the second one has a transfer function of say g2, and so on and so forth, and the nth one has a transfer function of gn, let's say. Yes, actually that's the thing. The equivalent structure is again a black box model of this. Keep this in mind. So that's a very fantastic question. What happened to the comparator? So Satyam is asking that if we do the equivalent modeling here, we are completely kind of getting rid of the comparator again. Yes, that's one of the objectives. One of the objectives in the black box modeling approach is to get rid of all the internal complications and represent the whole thing as something that interacts with the input and produces the output. Right? So in a sense, this comparator block was absorbed inside this model. So this model actually has absorbed this comparator block. Okay, so that we have a black box model. So that's the beauty of the black box model. So when we have the black box model of this whole thing, the equivalent model, we don't really need to know the internal intricacies, what we had internally in that model. We don't really want to know. We only are interested about how it interacts with the input and the output. And as long as that's not wrong, it's fine, right? It's fine. Just like, so for example, I want a 2 kilo ohm resistor. Maybe I don't have a 2 kilo ohm resistor at hand. Okay, so what can I do? I can just put two 1 kilo ohm resistors in series and put them in the circuit, and circuit will never know. The circuit will never know that instead of putting a 2 kilo ohm resistor, I had put two 1 kilo ohm resistors, because you can't even buy a 2 kilo ohm resistor. Okay, you can buy 1 kilo ohm resistors. You can buy 2.2 kilo ohm resistors. This is again by convention. The idea is that if you don't have a 2 kilo ohm resistor, you can just put two 1 kilo ohm resistors in series and put it in the circuit will never know. Okay, so as far as the input and the output are concerned, they never know that whether this was the circuit or this is just the circuit. Okay, that's the idea here. So in the black box model, we actually get rid of all the internal complications. I think I answered your question. Again, if you are not satisfied with the answer, you can once again ask me. All right, and then we would have different outputs coming out of this, right? So we would have a big summing point here, summing block here. We would have a big summing block here that will help us sum up all the signals. And let's say this signal approaches here, this signal comes here, and we again once again have many others. All right, so that's the summing block. And say these are the plus sign, say these are the minus sign, say these are the plus sign, I don't know. And of course there has to be just one output, right? That's the one restriction for a summing block. It can only have one. All right, so again, thank you for confirming that you understood. Again, here the output y will be equal to G1. Before I actually write down the output, what is the signal here? That's going to be G1x, because this signal x appears everywhere, right? X, all of them have x. So this is going to be G2x. Similarly, this is going to be Gnx. That way, of course, the output is going to be G1x minus G2x plus Gnx, and so on plus Gnx. All right, so that way this is going to be something like G1 minus G2 and so on, I don't know, plus Gn. And so this is equivalent to having a system whose transfer function is just something like G1 minus G2 and then whatever plus Gn. So if I have this system or this equivalent structure, as far as the input and the output are concerned, they won't know the difference. Okay, so this is x and this is still producing the same y. All right, let's hold on for a second. All right, so understandable, I hope. All right, oh, just hold on. Nice. So you understood this part, right? Someone is saying 1 by G1 plus G2. What? Why are you getting 1 by? Don't think about these as resistors. Okay, these are not resistors. Okay, just try to understand this properly. And okay, and here comes the last one, the standard feedback block, standard feedback system. Okay, in a feedback system, again we discussed this in our last class. We have a controller, then we have a system that we want to control, which is called the controlled system, and that produces the output. Okay, and here we have a reference input that is denoting what we want, and this is the comparator here, which is comparing these signals. And what are these? A feedback from the output of the system. So that's again the feedback structure. We discussed all these things thoroughly in the last class. Okay, so we call this signal R, stands for the reference, also called the input to the system. Okay, so this is again the desired output. The input is the desired output, and this C is a controlled output, controlled variable, or it is the output of the controlled system. So, and this is the controller, this is the controlled system. Okay, now of course, if everything is linear and time invariant, they will be expressed by their transfer functions. So assuming that this one has an impulse response of g1t, this one has an impulse response of g2t, they are Laplace transforms at their transfer functions. So I would just call this g1s, this is g2s, and of course similarly, if this has a impulse response of ht, its Laplace transform would be hs, so the Fourier transfer, so the transfer function would be hs. Okay, so that's the understanding here. Again, all these things are in the frequency domain. Everything has s in it. Okay? But we can just skip the s. Okay, I don't want to write the s everywhere, so you can just keep that in mind. You can actually skip the s because this is implicit. Everybody understand that. So this is the negative feedback loop. You can see we are comparing it. Okay, so whatever feedback signal comes in gets subtracted from the reference signal. That's why it's called a negative feedback. So the feedback becomes negative here. So whatever signal appears here, we call this the actuating error signal, and the actuating error signal is the difference between the reference signal and whatever feedback signal comes in. We call this B, right? So that's the error signal, actuating error signal. Okay, and this is again the manipulated variable. This is again the manipulated variable. This is ms. Okay, and this is the control variable, right? Now before we proceed with this, let me ask you a question. Before I try to simplify this whole thing, is there a way in which you can apply the previously learned simplification techniques? So you already learned two simplification techniques, one in Cascade, one when two transfer functions in Cascade, and one when two transfer functions are in parallel. So can you apply any of those two techniques here before I actually try to simplify everything from scratch? Can you apply any of the two techniques that you learned so far in this before we proceed into simplifying all this? Okay, I will just wait for a minute so that you can answer. Okay, so those who are saying Cascade, yes, you are right. These two are in Cascade indeed. These two are in Cascade. That's correct. But some of you are saying that, okay, these two might be in parallel with these, right? That's not the case. These two are not in parallel because in order to be in parallel, they need to have the same input. This is called a parallel topology because they have the same input. See, they have the same input. So x going into this, also x is going into this. So they have the same input. Okay, that's why we are calling them to be in parallel. Okay, here also all of these blocks have the same input, right? But if you are saying that these two blocks are in parallel with this, then you are wrong, because you see that this is the input to this block, this is the input to this block, and this is the input to this block. All right, so the inputs are not the same to any of the blocks, so they are not in parallel. Okay, but instead you can see these two are in cascade because the output of one of the blocks, the output of this block, goes into this block as the input of that block. So these two are indeed in series, or rather cascade, not series. These two are in cascade, and there is nothing called series. Just in mind, just keep in mind. So these two are in this cascade configuration, right? All right, so cascade configuration. So let's simplify this. Let's simplify this, and let me just copy and paste this because it is easier to copy paste. Yeah, only cascade. So it's these two are in cascade. So let's draw the equivalent structure here. All right, so these two are in cascade, and as obviously, then we can actually convert them into a single block. Okay, we can convert them into one single equivalent block. That's one equivalent block. Again, if you have any query, any confusion, feel free to ask. Keep on asking questions. So this is going to be G1S times G2S. G1S times G2S. Again, we can actually get rid of the S. Okay, someone is saying, what is the difference between cascade and series? Yes, there is a very subtle difference, cascade and series. You see, if I think about this, cascade tells you that the output of this system, okay, sorry, cascade here, okay. That's a big question. So what is the difference between cascade and series? Okay, there is a very big difference actually. Okay, let me just give you this idea here, ask you this question. Okay, these two resistors are in series, say. Okay, these two resistors are in series. Okay, right? Now tell me, what is the input to this circuit? Input to this system. The input to this system is this voltage V. And what does the input apply? The input applies on the whole system. Input applies on the whole system. You understand what I'm saying? The input is applying on the whole system, entirety of it. Okay, and then the output of this goes through this, and so on and so forth. Okay, but the thing is, what is the output of the system? Output is this current I. You see, in a series structure, the output is the same for all of them. So the same output passes to all of them. So same current passes to all of them. Okay, and the input is applied on the whole thing. The input is applied on the whole thing. But in a cascade structure, the input is applied on the first one. Then the output of the first one goes into the second one. The output of the second one goes into the third one. Okay, so their inputs are different. Their inputs are different. But here you see everything together gets one input. Okay, and the output of the whole thing is the same. So the same current actually passes to all of them. But the same output is not. So the output of all the blocks are not the same. Okay, because they are getting different inputs altogether. So that's the difference between a cascade and a series structure. In a series structure, everything is excited with the same input, all at the same time. Okay, so the voltage is actually divided by these series elements. Okay, so if I have something in series, then whatever input comes into the system are divided by the elements according to their nature. Okay, so the input is actually input voltage is divided by these resistors, right? So here something like that does not happen here. Okay, the input is entirely taken up by the first source, first element, the first block, and then it generates some output, and that goes into the next block, and then it generates some output, and that goes into the next block, and so on and so forth. That's the difference between a series structure and a cascade structure. Okay? And I'm going to explain later on why we don't have a series structure. We don't even have a series structure. But there are certain books which often call this structure to be the series structure. So this is like having two resistors in series, something like this. So the voltages, so the signals are added up here. Okay, this you might get confused by assuming that this is kind of a series structure, having 2 plus here, kind of representing a series structure. No, these are parallel structures. Okay, these are parallel structures because these are having the same input. So when two elements get the same input and their outputs are summed up, then that's called a parallel structure, because it is like the same thing here. I have a voltage source here, and say I have 2 resistors. Okay, this is called a parallel structure because both of these resistors are getting the same voltage V, and the current will be equal to the current I1 that passes through the first resistor and the current I2, the algebraic sum of these. Okay, I1 plus I2. So it is like that. See, this is not a series structure. Instead, this is a parallel structure because the input are the same for these two. Okay, so I have two resistors. They have the same voltage, just like that. I have two blocks here which get the same input. Okay, and the output, which is the current in this scenario, are summed up as the total current of the system. Similarly, the output of these two blocks are summed up. Okay, and you get the output here. So this is again a very concrete example of a parallel structure. Even though you see a plus sign here, don't ever confuse it with a series structure. All right. So let's go back to this. So we can construct this equivalent model of this, right? This equivalent model. So G1s and G2s multiplied here. Of course, that's an equivalent structure here. We can go one step ahead and actually copy this once more. We can even go one step ahead and copy this once more, and let's call this just G, and noting that G is nothing but G1s, G2s, the product of these two. Okay, nothing but the product of these two. So we can actually say something like that. All right. So now let's go back. So this is the signal C that is appearing here. Okay. So one of you have already got close to the very answer, but not quite. Not quite. Yeah, you got the correct answer. Yes, thank you. One of you got the correct answer. Thank you. So now here, what is the output here? That's H times C. The output is H times C. I'm not writing S anymore. Okay. So here E will be R minus HC. You see that C was the input here, so the output here is HC, and that's equal to B essentially. We call this B, so that's equal to B. So this was R minus B, so this is R minus HC, right? So that's R minus HC, right? And what is the output of this block then? So this is going to be G times E, okay, G times E. But what is E? E is R minus HC. So this is R minus HC. Okay. This is R minus HC, and that's equal to C. So what we get essentially, we get C is equal to G times R minus HC. Right? But that's it. That is what we call C. Right? So of course we can now do simplification on this, and we can actually write down that C is equal to GR minus GHC, and out of this we can actually bring this C to the left hand side, this term to the left hand side, and that way we're going to have C plus GHC, and that becomes GR. And now we can factor out this C here, and if I factor out this C here, I have 1 plus GH. Okay, and on the right hand side I have GR. Yes, right? And then we can write C by R, or rather let's write C, that's equal to G by 1 plus GH times R. Now what is the input? Input was R. What is the output? Output was C. So now what we can say, the output C is actually, if I simplify this completely, the output C is G by 1 plus GH times R, right? The output C is like that. So that way we can actually construct an equivalent circuit of this whole thing, equivalent structure of this whole thing, where input is R. This is the equivalent block, and the output is C. Okay, whatever output, and the structure here has a transfer function of G by 1 plus GH. That will yield the same result as far as the input and the output are concerned. Once again, I am considering everything to be inside a black box. So all these things are inside a black box. Only the input and the output are externally visible. So under that scenario, this is the equivalence structure. All right. So far, any question? So if you have understood this, I have a homework for you. And in the homework, you need to figure out the equivalent transfer function for this structure. So I'm just putting the cascade already inside. So that's G1 times G2. Assume that. The very same thing, only that instead of being a comparator, this is a summing block. So both of them have the plus sign. So this is R, this is C. Okay. So calculate the equivalent transfer function. Question is, calculate the equivalent transfer function. All right. No problem, right? Okay. So again, ask anything that you might want to ask. Now, once we have these ideas once we understand these ideas, we can actually get to work and actually solve a real problem. Okay. So if you have checked the Google Classroom, you would have seen that I have posted one problem set. Okay, and that problem set will consists of all the topics that we are going to cover in the theoretical portion of this subject. Okay, so let me just that's a problem set. So this will actually involve everything that we're going to discuss, the problems from every part of the course. And so I gave you this before I actually start the actual class. So today we're actually starting the actual theoretical discussion, right? Proper discussion. So all these are the exercise problems that you probably are going to need to solve. Okay, and all the topics that we are going to cover in this course. All right. And here, let's solve one problem here. Let's take the first one, okay? Because it's an easy one and we can actually get to it. So idea is to find out the equivalent transfer function. So everything that's, so this RS, that's the input signal, and that's going into the summing block here, or the comparator here, okay? And all these things are happening, and C is the output, okay? And C is the output. So I want to construct one single block out of that. So I want to consider everything to be inside a black box, and I want to construct one single block out of that. Okay, so that's the objective of what we are going to do right now. So we are going to use whatever techniques we learned, okay, and then we are going to rather simplify this structure. Right? We're going to simplify this structure. All right, so that's understandable, right? Okay, so we are going to simplify this, and as homework, you would have to solve these problems. And again, I would help you these, so don't worry. So if you need additional classes, so I told you earlier that we're going to arrange additional doubt clearing classes. Maybe there we are going to solve a few more. Okay, if you are somehow unable to solve any of these problems. Okay, so let's solve the easiest one here in the class. So that's the problem we are going to solve right now. All right. So the question would be very simple, obviously. Uh, Calculate the equivalent transfer function of the following system. Obviously, that's going to be the question. All right. So with that being said, let me ask you some simple things. Um, do you see any structure? I mean, do you see a cascade? Do you see a parallel structure? Do you see a feedback structure here? Okay, that's my question here. Do you see a feedback structure? Do you see a parallel structure? Or do you see a feedback structure? A cascade structure? Anything? So let's talk about these. You might say, okay, these two are in cascade because indeed the output of this is going as the input of this, right? So you might say these two are in cascade. Unfortunately, that's true, but we cannot actually simplify these two blocks. Unfortunately. Why so? Because if we, again, you know that if we consider this to be a black box and simplify this as a cascade block, then what happens? Everything that is there inside vanishes and we just have a single transfer function. Okay. Then what happens to this point? This point is called a branch point. A branch point is a point from which we take signals out of. Then what happens to this branch point? That branch point also vanishes. So if I apply a cascade topology here, okay, in that case, that point actually vanishes. So this line would have nowhere to go. Okay, so if I apply cascade, then this line would have nowhere to go. Right? So we cannot directly apply a cascade here. Understandable? Now, some of you are saying that we have a feedback loop. Yes, indeed, we have a very big feedback loop. See, this is a feedback loop. Okay, so that's a feedback loop, right? That's a feedback. But you see, you are right. These two are in cascade, technically speaking. These two are in cascade. Okay, and there is a feedback loop. Unfortunately, if I construct the feedback loop, okay, and represent everything using one single transfer function, then we once again have the same problem. The problem is that this entire thing is inside the feedback loop, right? This entire thing is inside the feedback loop, and as such, whatever we have inside will vanish into the feedback loop. So what will happen to this point, to this signal that is coming out of this and going into the feedback loop? Where will it go? It will not have any location to go, right? So because of that, we cannot actually construct the feedback loop out of this. Okay. In a very similar fashion, you can say that there is another possible feedback loop which goes this way. So this is the forward path, and that is the feedback loop. Unfortunately, the same dilemma we have here. Okay, you see, if I construct the feedback loop out of this, say that's the feedback loop. Okay, then once we write down the equivalent transfer function, everything that is inside actually will vanish, and as such, everything that is here will vanish. Okay, right? So we have the same problem once again. Question is, where will this signal come out of? Okay, if I represent everything that is there here with the same single transfer function, okay, that has one input here, one output here, then where will this come from? Okay, if I write a transfer function, big transfer function GS here, okay, then where will this come from? Nothing, right? There would be no option possible for that. So none of these options directly apply here. None of the simplification techniques would directly apply here because we have these branch points or the summing points interfering with our simplification techniques. So this is the branch point interfering with this cascade. Okay, this is summing point interfering with this feedback. Okay, also with this feedback, this branch point is interfering. So we have all this interference. So we have to kind of simplify the idea here. All right. So, I apply the idea from scratch to figure this out. All right. So let's see what we can do. Before we actually proceed with this, I have to actually draw this manually because otherwise I won't be able to solve this. Just hold on patiently for a moment. I mean, drawing these things on a using a pen on a paper is easier than drawing these things on a computer actually. Okay, and then we have another blocks. Block here. All right, I think I have got it. So let's draw all the signaling paths. Okay, that's one feedback, which is going from this to this. Let me actually pull this up. Okay. And it's that actually. You notice the direction of the arrows. Okay, if you somehow change the direction of the arrow, the whole thing actually changes. All right, and we have another feedback here. Okay, you see that signal has been tapped from here. Signal has been tapped from here, and we have one final feedback on the whole thing. It's coming from the same point here. All right, so that is the structure here. So G1, G2, G3, H1. So that's going to be G1. Okay, G2, G3. That's H1. And that's H2. That's a feedback loop. I believe you understand that's a feedback because it's taking the output signal and bringing that back to it. So with a minus sign again. So it's a negative feedback. Okay. This is again a part of a feedback loop because just like that it happens. Same thing here. We have three feedback loops here. So that outermost feedback loop will be taken care of the last. So that's C and that's R. We are not writing, sorry, that's C and that's R. We are not writing any implicit S transfer function variable because I don't want to. Okay, that's the easiest explanation. It is understood that we are doing everything in the frequency domain, so I don't want to or don't have to write S every single time. All right, so that's the structure we have, right? So I already explained that it's impossible to actually apply any topology right away. Okay, so we have to kind of simplify this a bit so that we can actually apply a certain topology here, right? Now let's notice that, okay, I think I should zoom this up. This was better. All right, so let's start applying that idea. Okay, again, whatever we derived moments ago was based on the equivalence of inputs and output. Okay, so based on equivalence of inputs and outputs, and understanding that, we know that as long as we don't change the inputs and outputs, we are fine, right? We are all good to go, right? So think about this branch point here. Okay, think about this branch point here. This branch point was kind of defeating our objective to merge these two blocks, right? I mean, if I didn't have this branch point here, we could have just merged these two blocks and made one continuous cascaded block, right? One equivalent cascaded block. But we couldn't do that because of this branch point here. Because if we construct the cascade equivalent here, this branch point will vanish. So let's try to move this branch point. Now, what do I mean by saying we want to move this branch point? What do I mean by that? We want to keep the equivalence, the input-output equivalence intact. Okay, let's say the signal that appears here, at this point is called X. Okay, the signal that appears here is called X. So X is the signal that goes into this as well. So what is the signal that is coming out of this? That's going to be H1X. Okay, if X is the signal that's going in, then H1X is the signal that's going out. Right? Now, thing is, what is the signal that is appearing here? What is, if this is X, what is then the signal here? The signal here is G3X. So G3X will be, of course, equal to C, but let's not think about that right now. But the signal here is going to be G3X because that's the output of this block. The input of this block is X. The block has a transfer function of G3. So the output of this block will be G3X. Right? So with that being said, let's do one thing. Let's copy this picture and paste it and try to draw one equivalent structure here. Let's say I don't want this line to be here, but instead, what if I have this line from here? If I had this line from here instead, okay? If I had this line from here, so the same thing. Now, instead of writing it here, if I move this, so the summing point was here, so the branch point was here, I have moved the branch point here. Okay, now what is the problem? The problem is that the input to this block is no longer X. Whenever I was drawing this signal from here, it was X, but now this is G3X. All right, so what is going into this? G3X is going into this. Okay, G3X is going into this, but the thing is, I want its behavior to be identical. I have moved the branch point, so I have changed what input it is having. Previously, it was having the input X because that was the input to it. Now, I have changed its input. Okay, but I want to keep the relationship intact. I want to keep this the output. I want to keep this as the output. So I want this to be the output no matter what. Even if G3X is the input. Just hold on. All right, so now question is, I really don't know what I can do, but the thing is, I can think about something. See, I want this output to be here, right? And this is now the new input to this structure. Okay, question is, what kind of transfer function do I want here? What kind of transfer functions do I want here? What transfer function do I want here? I cannot have H1, because if I have H1, I would instead have H1 G3X as the output, which I don't want. But surely we can have something else that will help us do that. So instead, if I have H1 by G3 as the transfer function, so if I have H1 by G3 as the transfer function, then if this is the input to this, then H1X will be the output, because H1 by G3 times G3X gives you H1X as the output, right? So now what we have done, we have moved this branch point like this from here to this point, and that way we now have an equivalent transfer function here. So this is again an equivalent transfer function resulted from moving this branch point to the right. Now the relationships are still holding, and we have gotten rid of this branch point here. So these two are equivalent. So this block diagram and this block diagram are equivalent as far as the input and output are concerned. I don't want to know what is happening inside. As far as the input and the output are not changed, their behavior is not changed, we are happy. Okay, so that is exactly what we are ensuring. We are ensuring that this was feeding back h1x, this was feeding back h1x, this is still feeding back h1x. What input it is taking has changed, but its feedback has remained the same. Whatever output it was giving has remained the same. Now with this structure, now we have an advantage. The advantage is that we actually had one problem. The problem was that there was a branch point which was interfering with this cascade structure. Okay, this branch point here was interfering with this cascade structure. Now we can actually completely get rid of this. Forget about whatever signals we considered. Okay, and we can completely get rid of this and make an equivalent block out of that. So I had G1, G2 and G3 transfer functions in Cascade, and we can actually construct one equivalent block out of that. And that equivalent block would have a transfer function of G2 times G3. All right. So that's the equivalent structure here. All right. Any confusion there? Now we can actually, we have actually gotten rid of that. And by doing that, by doing this, this one here, we see we have opened up another opportunity here. What is the opportunity? Opportunity is that we have a feedback loop. See, that is the feedback loop. Okay. So this is the feedback loop, except it is drawn the other way around. Okay. We could have drawn this from below. Now we have instead drawn this from above. Okay. So this is an equivalent. So this can be considered to be an equivalent feedback block here. All right. So this can be assumed to be an equivalent feedback block. So this whole thing is an equivalent feedback block. So what we are going to do, we are going to simplify this feedback block into one single block. Okay. Of course, we can do that very easily. I think I have to get rid of this. Copy this and hold on. Okay, just let me draw this once more. So I was talking about this feedback loop. Yes, the bottom feedback, no, it won't change, because you are saying that, okay, if I construct a feedback loop out of this, what will happen to the bottom feedback loop? I mean, you are talking about this, right? The thing is, by getting this feedback loop into one transfer function, you see, I don't have any problem, because you see that this junction point is not removed. Actually, this junction point is not removed, or rather this branch point is not removed, because this branch point, what is the value of the signal here? This branch point has a value of signal C, right? And this is C. C is the output. The output is always available. Input is always available. The output is always available. Okay. So yes, so we are not actually getting rid, even though it looks like we are getting rid of this branch point, we are getting rid of this branch point. It looks like so, but it is not actually so, because this branch point is appearing at the output terminal here, right? We are not getting rid of that branch point. It is there. Okay. So we are getting rid of this feedback loop, and you see the branch point did not disappear. So we have one feedback loop for describing that whole portion there. So nothing wrong happened to the lower feedback loop here. All right. So now, of course, the equivalent would be, of course, you can calculate, consider this to be G, this to be G, and this to be H. The equivalent, so this is a negative feedback once again. The equivalent would be G divided by 1 plus GH. So here G is G2, G3 divided by 1 plus GH, and G is again G2, G3, H is H2. So that becomes G2, G3, H2. So that's the equivalent here. So again, this feedback loop is still there intact. And as a matter of fact, we are going to talk about this feedback loop next. Okay. We are just going to take care of this feedback loop next. Okay. Let's just copy this and paste this. I don't think I can paste it. Okay, see. Yeah. Okay. Now let's think about this feedback loop once again. So now here, here you can see we have a feedback loop. So that's a feedback loop. This whole thing is a feedback loop. Once again, we won't be getting rid of this by considering this as a summing feedback loop. We won't be getting rid of this branch point because that branch point is at C, right, at the output. So the output is always there. So nothing wrong will happen with this feedback, with this outer feedback. Okay. So now we are going to consider this whole thing as the feedback loop, as the feedback loop. But before we can do that, we have to notice one more important thing, is that these two are in cascade. That these two are in cascade. So let's do that first. Okay, these two are in cascade. Okay, let's do that first. So get rid of these. And of course, cascading means this transfer function will multiply with this transfer function and result into the product of those two transfer functions. So let me just draw this in a good way. Okay, so this becomes G1, G2, G3. G1, G2, G3 divided by 1 plus G2, G3, H2. G2, G3, H2. Okay, so that's the equivalent there. I think you are getting this, right? And then of course we have a feedback loop. And this is the feedback loop. As I was saying, let me just copy this before I actually draw the feedback loop. Okay, so we have a feedback loop, as I was saying here. So that goes like that. That's a feedback loop. Again, we are not doing anything cruel to this, because even though this branch point is gotten rid of, but still this is corresponding to the output C. So that branch point would actually be still there. Okay, so that's the feedback loop. And in this feedback loop, we are assuming this to be the transfer function G and this to be the transfer function H. Okay, that's G and that's H. So if that's G and that's H, we know the equivalent transfer function for this whole thing is going to be given by G by 1 plus GH. But we're assuming this to be G and this to be H. So let's write those down. Okay, so that's going to be G1, G2, G3 divided by 1 plus G2, G3, H2 divided by 1 plus, again we are considering this to be G. So have that. Times H, and H is H1 by G3. Okay, so now let's simplify this. I think we can cancel out this G3. One G3 can cancel out. The denominators will be the same, so they can also cancel out, and that way we would be having G1, G2, G3, simple algebraic simplification. And that's why this is algebra again. We're adding, subtracting, doing multiplication and division, nothing else, right? So that's why this is block diagram algebra for you. And if we take the LCM here, the same factor will cancel out. So this is, again, these two factors will cancel out, and if you take the LCM here and add these two ups, that's going to be 1 plus G2 G3 H2 and plus G1 G2 H1, G2 G3 H2 plus G1 G2 H1. Yeah, I think we have done it correctly, right? So the equivalent here, the feedback loop, the equivalent transfer function for this entire feedback loop. So if I get rid of this, the equivalent transfer function for this feedback loop would be that. So if I haven't made any calculation or mistakes, which I often do, so it's your duty to figure out if I have made any mistake there in calculation. I really told you that I am really very good at doing calculations, so I always do everything using a computer. All right, so that's the equivalent transfer function. So let's bring it here. All right, fine. And now we have a single feedback loop where there is no transfer function here. But if I don't have any transfer function here, question is, can I assume that we actually have a transfer function whose gain is just 1? That way, whatever signal comes in here, exactly the one that goes out of that. So that's the transfer function, which is equal to 1. Okay. So let's go back to our topologies first, once again. And here, let's say H is equal to 1. So if I have H is equal to 1, in that case, we have this sort of a structure. If H is equal to 1, in that case, we have a transfer function G there. Okay. And this is again C, and this is again R. And if H is equal to 1, that's the feedback transfer function, which is equal to 1. In that case, we just draw it like this. Obviously, right? We just draw it like this, because if H is equal to 1, if I just draw it 1, so I get C goes as the input here, and C is the output that goes into the comparator here. Of course, instead of doing all that, if I just draw a line out of that, same idea is still there, right? So H is equal to 1. Now, of course, the total transfer function here, the equivalent transfer function would still be G by 1 plus GH. Now here H is equal to 1, so this is just G by 1 plus G, because H is equal to 1. So this kind of structure is very common, so common in fact it has a very special name of itself. It's called a unity negative feedback loop. So unity stands for, yes, the feedback gain is unity. So instead of having a transfer function here, we just have 1. So it's called a unity negative feedback loop. Okay. So let's get back to this. So here what we have is a unity negative feedback loop. So I don't think I have to draw this 1 anymore here. All right. And with that being said, let's consider this whole thing to be this gigantic G here. Okay. This whole thing to the transfer function G here. And let's bring up the calculation. So this whole thing is the transfer function G, right? That's G, and that's the unity negative feedback. Okay. So with that said, the total transfer function, which is denoting the ratio of the output to the input, which is ultimately C by R, the total transfer function of that. That's going to be the unity feedback loop of this, loop out of this. So which is going to be G by 1 plus G, and now of course G is this quantity. So let's copy this quantity. So that divided by 1 plus that. Okay, so that's the simplification. And again here we can actually once again simplify this. Not so very, it won't be very difficult. Okay, we can simplify this. Since the denominators will be the same, they will cancel out with each other. And in the denominator we have 1 plus G1 G2 G3 plus G1, G2, H1. Let's move this to the downside. Okay, and we have, so 1 plus G1, G2, G3 plus G1, G2, H1 plus G2, G3, H2, and on the numerator I have G1, G2, G3, G1, G2, G3. Yeah, that's a total equivalent transfer function. So if I get rid of this entire feedback loop, so equivalently I just have the input, the total transfer function, and the total output. So this is R, this is C, and the transfer function is going to be this. So that's the ultimate equivalent structure that we sought to figure out. So this is the equivalent transfer function. This thing is the equivalent transfer function of the original system. So we had the original system that looked like this. So we had these many structures inside. So we wanted to keep R and C intact, and we wanted to simplify the internal structure here. So this is called a block diagram reduction. So we reduce the block diagram into a single block. Okay, single black box here. Okay, so this transfer function does not tell you anything about what there was, right? This transfer function does not tell you how it was constructed. Okay, this transfer function does not tell you how it was constructed. Okay, but it tells you that as far as the input and the output are concerned, this is the relationship between them. This is the relationship between them, right? And this file will be available with you right at the end of this class. Let's see this file. Sorry. All right. So I believe you understood this. So I would just wait for two more minutes, and I would just give you your assignment here. And some of you might find this this way of solving, doing this block diagram reduction a bit difficult, right? Some of you might find this a bit difficult. For them, I have a good news. The next day, in the next class, like on Wednesday, we are going to see another technique that would allow us to solve this problem. Okay, doing a block diagram reduction in just a single step. Okay, so on the next class, we are going to learn a technique that will allow us to do this block diagram reduction. So all this complicated calculation, step-by-step reduction, using a single step, in a single step. Okay, so we are going to learn that technique in the next class. Okay, but in any case, in order to verify your results, you still need to know this. So your homework would be this. These are assignments once again, not just simple homeworks that you may or may not do, but you have to do this thing because these are your assignments. Again, question is, calculate the equivalent transfer function between C and R. Okay, so basically output by input. So the whole system needs to be simplified using the block diagram reduction techniques that we learned today. So we learned block diagram reduction techniques, and I'll be waiting here for just one more minute. I know it's already over the standard time here, and if you have any query, just feel free to ask. Again, this file will be given to you in your Google Classroom, as well as it will be available in the video description. So later on, after the end of the semester, I will archive the Google Classroom class, and then you can only access these files from here. Okay. So any question? But don't worry, we're not going to end everything right here, because the idea is that if you find it difficult to solve problems by yourself, I would of course arrange additional classes. Okay, we are not going to move forward unless you are comfortable with the topic that we covered. All right, So anything you might want to ask? Otherwise, we're going to end today's discussion at this point. Thank you very much for being here for so long. I'm just waiting for any question. All right, so if you don't have any more questions, we're going to end this stream here. Thank you very much for being here. I will see you in the next class on Wednesday.